So finally, I want to teach you guys about how to use inverse functions when we're working with areas and volumes. Yeah? And before we do that, let's just have a little reminder of the equations that we do need to use for areas and volumes. So starting off with area, remember that's just integrating from two lines, so B and A. And the important thing to remember is that if it says it's bounded by the x-axis, we use dx, and when it's bounded by the y-axis, we integrate in terms of dy. Now, the volume equation a lot of students have trouble with, and it's all because of this pi at the front here. It's just so easy to forget, so just be really careful about that. And it's also, remember, it will be the equation squared, so the whole equation squared as well. And the same principles apply to that than it does to area. That is, if it's rotated around the y-axis, it'll be dy. Rotate around the x-axis, it's going to be dx. Yeah? All right, so a little reminder there. Let's go through questions now. Okay, so question 35, I want you to find the area that's being enclosed between this curve here, the x-axis, and also the lines x equals to 0 and x equals to 1. All right, so before we start, we actually need to set up the equation. So we've just been given words here, so we need to put it into an equation. So we want to find the area, so we're going to be integrating this. And it's between 0 and 1, which means we'll be integrating from 1 to 0. And then finally, it's in terms of the x-axis, so I know it has to be dx there, yeah? And because this equation here is already in terms of x, that means I can put it straight into the integration there. All right, now having a look at this equation here, what does it remind you of? Exactly, it reminds you of what happens when we integrate that and becomes inverse sine x on a. So in this case, a is quite easy, it's just 1, yeah? So this just becomes inverse sine x from 1 to 0. And we can just now substitute that in. So inverse sine 1 minus inverse sine 0, and just work that out. So we know inverse sine 0 is just 0, and inverse sine 1 is 90 degrees, so that's pi on 2. So your answer should be pi on 2 units squared. So it's really important you always remember this units squared here, because otherwise you're going to lose half a mark, and it's just not worth it to lose half a mark for something like that. Okay, so things to remember for this question, that setting it up is probably the most difficult part. So as long as you set it up correctly, it really is just standard integration. So remember, just check that x-axis has to be in terms of dx, make sure the equation in terms of x. Yeah, that's basically, and it's a basic error that people tend to make. All right, so that was question 35. Let's move on to question 36 now. So here we want to find the area under this curve, and between the lines x equals to -2 and x equals to 2. So this curve, if we want to find the area under it, that's going to be enclosed by the x-axis, yeah? So that means in terms of dx. So I want to integrate from 2 to -2 in terms of dx, and this equation here. And this looks similar to when you integrate to get inverse tangent, doesn't it? The only difference is we usually want 1 on top, and here is 16. And that's easy enough to fix. All you need to do is just take 16 out the front there, and we have 1 up the top. And because 4 is 2 squared, I've just worked out a equals to 2, yeah? And remember, when you integrate this, you get 1 on a times inverse tangent x on a, yeah? So remember how I said a lot of people forget this 1 on a, so just be careful to make sure you put the 1 on 2 in front there. And it's always easier to take it outside of the bracket, because then we don't need to subject it to this when we substitute it in. So that just becomes 8. Substituting in 2, -2, you get inverse tan 1 and -1. Remember, with inverse tan of -1, we can just make that negative inverse tan of 1. So essentially all I've done is just take the negative out. So that negative and that negative is going to make it a plus, yeah? That's pi on 4 each, so that's just pi on 2 times 8 just gives you 4 pi units squared, okay? So looking at this, you knew it was going to be inverse tangent, but we just had to remove the 16 before we could apply the formula, okay? All right, last question here, question 37. So here I want you to find the area that's been bound by this curve, yeah? The x-axis, x equals to -1, x equals to 2, and this area is actually rotated around the x-axis. So that means we want to find the volume of the solid, yeah? Do you guys remember the volume equation? So that's volume equals to pi, and it has to be this equation squared, which actually ends up being very useful, because if you look at that, that's neither inverse sine or inverse cosine, because you need a negative in there. But you can see that when we have this, yeah, so remember your pi at the front, and we square that, this becomes 1 on 1 plus x squared, which is our inverse tangent, yeah. Okay, so I can just make that, because a just equals to 1, so it's quite easy. Just inverse tangent x. Don't forget your pi at the front. And there's no point writing the 1 on a, because that just becomes 1 on 1. Okay, so that's why it's just inverse tangent x by itself. Now, substituting in 1 and -1, remember you can just take that negative out, so the negative and negative become a positive. That becomes pi on 4, and that's pi on 4 as well. So this is pi on 2, but because we have this pi in front, we multiply it and you actually get pi squared on 2, and it's units cubed because we're working out the volume. So with this question, you just need to remember the volume equation, and just be careful to not think this is going to be inverse sine, because it's a plus rather than a negative. And when you do square it, it's quite obvious that it's going to become inverse tangent when you do integrate it.